Okay, so I'll begin here. The first thing we'll start with, I'll just go over what this is going to cover. So I'll start just by going over basic calculator setup, some things that really helped me setting up my calculator when I was figuring out this exam, and then I'll kind of go through a good amount of practice problems that will that's going to be similar to what you're going to see on the exam. So beginning here with calculator setup. Now I'm doing this with the TI-84. This should be the same with like a TI-89 or something anything around there, TI-83. I know we can't use Inspires, so that would be a different ballpark, but this should work for most people. So when we're setting up the calculator, we need to make sure that our mode is in degrees for this exam, especially because that's what we're going to be using, our degrees. So if you see an angle with no degrees on it, then you can assume it's in radians, but for the most part it won't be. You want to make sure and so you can do it in real. You can use real, or you can use the angular form. I prefer to use real. I like using A plus BI rectangular form. And you can use either one. You just need to know how to convert back and forth between them. So yeah, now I'll show you extra storage kind of function that I use that really helps me out. So if you see on your calculator, you can do, if you just write in E to the pi over 180 I. So if you put that in your calculator, E power 180, pi over 180, and then I after it. And now you'll do, on the bottom left, you'll have this next function. It's going to be STO. You might, if you see at the bottom left, STO. And then I would store that under, I would store that, and then you'll do alpha, and then math. So if you do those, so you'll store it in what's variable A, basically, that's what you're going to see. Then you hit enter, and this will make sure you're in the modes we talked about at the top, the degrees, and then A plus BI. And when you do that, your A is going to be stored as E to the pi over 180i. Now, why is that important or interesting? So if you do, say we have 3 angles 60 degrees, if you do 3, and now we have it stored as A, if we do 3A to the power of 60, that will convert it to rectangular form now. So if I did 3A to the 60, I'd get 1.5 plus 2.6 I, or we'll start using J now for the correct notation. And that really helps out. The only thing with this, though, is for the exam, you would have to memorize this, because you need to clear out your calculator. So if you find it really helpful, it might not even be that hard to remember. But this really is helpful for just quickly converting. And you could try it, but that'll be really helpful for quickly converting between phasor and rectangular. So, so now I'll move on. I'll go to the complex numbers and phasors. So I'll kind of run through these a little quick. These are just practice. You could do it along with me. And we'll start. So I put the functions that you want to use for these. So like here we would have the square root of 3 squared plus 8 squared, right? That's gonna give us just about 8.54, and then arctan of b over a, 8 over 3, is 69.4 degrees. 8.54 angle 69.4 degrees. Don't forget that degrees sign. That's really important. If not, it'll be considered radians. So that one was straightforward and simple, but the other two I made specifically where we need to do something a little extra. So square roots are always going to make them positive. So we know that's going to be 16 plus 30 square root 16 plus 36, 4 squared, 6 squared, which is about 7.221. And now this is where we need to watch out for is we have arctan of 6 over negative 4. And that'll give us negative 56.3 degrees. Now this is okay, right? Like the magnitude cannot be negative. The angle could, but you could just add 180 degrees to it. That would keep us, that's in a good, the correct quadrant. I'll go over that. So we'd have 7.21 angle angle 123.7 degrees. That's when I add 180 here. And the last one you can do on your own, but I'll tell you 13.9, 149.7 degrees, and then you can just keep that. Here though, you're actually going to get negative 30.26, and I added 180. And I'm going through these really quick because this is just the review, like really basic review of it. I'd rather spend more time on the circuits. So always make sure to use the degrees and try to keep your angles in relatively between 180. So I'll put just the degrees. You want to keep it between negative 180 and 180. So if it was like negative 190 degrees, add 180 to it. So you get negative 10.
Why are we adding 180 to this last one? If the negative 30, isn't that like?
That would work. So you could do either one. And then this representation is not, it helps understand why we do what we're doing. Is we have our angle theta here and our A, B, and the imaginary axis, so B, and this, the Y is our imaginary, and X is going to be our real, so the imaginary J. And this is where the angles, that's why we're getting the arctangent of B over A. That's how we're getting these points. So if you do forget at any point or lose track, try and visualize that. That might help you out. Now next one is same kind of form, phasor to rectangular. You can do what we did in the calculator. or you can do the magnitude times cosine of theta, or cosine of the angle, and plus the magnitude of sine of the angle. So if we did 4 cosine 60, and then 4 sine 60, that would give us this equals 2, and this is going to be about 3.46. So we'll have 2 plus 3.46 J. And now if you wanted to check that, I'll do it. If you did 4a, so if we're going back to the calculator at the beginning, if we did 4a to the 60, to the power 60, that should be exactly what you get. So that that really helps out instead of having to type the whole thing out. You could do 4 cosine 60 plus 4 sine 60i, and you get that as well. But 4a to the 60, really, that's quick, and it might help you time wise. 5 angle negative 130, you could do the same thing. So I'll just do the answers for these. I was hoping to get a little more time, but 1 hour, I figure that going through this quickly gives more time for the rest of it. 1.73. And if we have 1, you can either do just the imaginary part, so just J, or we could have done plus 1J. That's the same thing. And you could do these quicker than I could using your calculator, quicker than I could even write it down. It's complex multiplication. The big thing to remember here is I think in algebra it's called foiling. So make sure that you don't, if you see 3 plus 2j and you multiply it, make sure you don't just distribute it or do something. You need to FOIL this out. So you're going to have 3 times 4, 12, and then you'll have the 3 times 3j, so we'll have 9j, 2j, 4j, 8j, and then this is the interesting part, and this is what's really cool, is we'll have 2j times 3j, which is going to give us 6j squared. Now remember that j squared is actually equal to -1. So this is really 6 times -1, so it's a -6. This is a -6. So now we can just add that to the 12. So we end up with 6 plus 17j as our final answer there. Remembering that j squared is -1 is really, really helpful. J to the 4th positive 1. That'll help out. You're probably not going to see more than j squared though. Complex division. This is also the same thing as like multiplication. We don't want the 5 plus 2j. We don't want the rectangle, the imaginary on the denominator. So what we're going to want to do is rationalize it. So you would multiply by the conjugate. So 5 plus 2j, we would multiply by 5 minus 2j on the top and on the bottom. On the top is easy because that one you can actually just multiply 8 in. So you get 40 minus 16j. But the denominator will be the same as what we did with the complex multiplication at the top. You need to make sure that you FOIL this out. So you'd get 25 minus 10j plus 10j. So that'll cancel, and then you'll get -4j squared, which would be +4. So you'll end up with 40 minus 16j over 29. And that accomplished exactly what we wanted it to. It got rid of the imaginary in the denominator. So now we just have it in the numerator. I believe, so we got one more part of the like before getting into the real circuits.
For the division, he always wants us to put it into decimals. So is he expecting us to do like 40/29 and then 16/29 and put it in decimal?
Yeah, then you could break that fraction up. Exactly, yeah. So you 1.38 minus 0.552J. So converting from time domain to phasor domain, this is still kind of following the same formula of what we've been going through. A big formula to remember, and maybe it might even help you just start the exam and write some formulas down. Omega equals 2 pi times the frequency. That's something you want to remember. And then you can divide by 2 pi to get frequency from omega, or you can do it vice versa, whichever way you need. So if we're given our frequency is 400 hertz, and we want to, so say we wanted to convert it to omega, so we can write out the time domain function. We have omega equals 2 pi times 400 hertz. To keep it simple, I would just do 800 pi radians per second rather than multiplying pi in there, so I don't have to deal with a bunch of decimals yet. And then we have 3 angle 60, and now this is pretty easy to write out. We'd have VT, we have our magnitude, 3 cosine. We know our omega is 800 pi t plus 60 degrees. Also, don't forget your degrees. You make sure we have that degree sign on there. Now converting to phasor is similar. So this one's a little different, because if we just write this out, we got our magnitude and angle. We'll have 12 angle negative 372 degrees. Now that negative 372 is fine, but we could easily write it as something else. I would add 360 degrees to it. So just bring it back around, and it would simplify the angle a lot. So we would have 12 angle negative 12 degrees. And you could do the next one same way, but this one's a little different because we have something else thrown on there. It's 14 sine. So you need to watch out that and make sure and see if it's in sine or cosine. So this one's 14 sine. So to change from sine to cosine, we're going to add 90 degrees to it. So we'll end up with VT equals 14 cosine. The 181 stays, the 14 stays, but the degrees changes. So we'll get plus 77 degrees. And now we can easily write this as 14 angle 77 degrees. What is phasor analysis used to find? And you may be asked this on the exam. It's used to find the steady state sinusoidal response of an RLC circuit. So that right there, that covers the generic like math stuff that you're gonna have to use the whole entire exam. The reason I went through that quick, just so we could get to the actual circuits. But if there's any questions, you can ask there. So now what we'll get into is, I'll start slowing down a little bit. This is what you're gonna start really seeing on the exam. This is gonna be very similar. So one of the first questions you may see is gonna be similar to what we just did. And I made this one difficult. You may have to do one or both of these. Is we wanna take this current and put it in phasor. So this is in time with respect to time. So you wanna, the first thing I would always look at, is it in cosine or sine? And now this one we can see is sine. So we can do just what we did with the last one, is we added 90 degrees. So you can add or subtract. We have IT negative 2.6 cosine 257t plus 30 degrees. Amps. Don't drop the units. We got to keep that amps on there. And now we have the, now I check the next thing I would see is the magnitude. So the magnitude of this is negative, and we do not want our magnitudes to be negative. We need them to be positive. The angle could be negative, the magnitude cannot. So to change that there, it's also just a similar angle change, is you can add or subtract 180 degrees. Here I would subtract 180. Because we added 180, we kind of go out of those bounds I was mentioning, right? We go into the 210 degrees. So I would go IT equals 2.6. So the negative goes away. Cosine of 257t minus 150 degrees amps. Awesome. And now that's looking pretty solid. And we can write it out as 2.6 angle negative 150 degrees amps. That's going to be the that's going to be describing it as a phasor, keeping the amps and going all the way down. Remember, side x is cosine x plus or minus pi over 2, which is 90 degrees. So that one's helpful. Make sure so really those are the main things, is making sure that that it's cosine and that your magnitude is positive. And then you can look at the degree at the end and make a decision as to whether or not it's in a good range. If you see like negative 600 degrees, then there's a pretty, you could easily change that. Mm-hmm.
So is it plus or minus power to?
Yes, so it would change it either way. So if you can see where if we drew it out and we had like the 30 degrees out here, if we subtracted 90, did I do that? Oh yeah, sorry, it was negative 60. Sorry, so if we subtract negative 60, my bad. So if we subtracted, we would go into quadrant 3. We add, we go into quadrant 1. So it depends on where you want to be. You could do either one. If I subtracted 90 degrees though, we would be negative 150, right? And if we're at negative 150, then we'd have the similar thing here, is it would be negative 2.6 cosine and negative 150. We could do 2.6 plus, and we would get positive 30 degrees. And if you look at this, is 2.6 angle negative 150 and 2.6 angle 30 would give you the same line.
Does it, okay, you're saying you could add 180 and get the same.
So 180 will change the magnitude. 180 will make it positive or negative, the magnitude of the angle. So if we're in quadrant 3, is the magnitude of the angle going to be positive or negative?
Negative.
Correct, right? Quadrant 3 is in the bottom left corner, so your x-axis is negative, your y-axis is negative. So the reason you add 180 is to get into quadrant 1, where they're both positive.
Okay.
You understood? So that's going back to looking at this, right? So we have our A and our B. So when the line was here, that was giving the A was negative. So we add the 180 degrees, and that would make the A positive. So that's why graphing it out, seeing it a little bit might help you.
What's you on?
Huh?
What's you on that?
So next thing is input impedance. The first thing I always do in these questions is we're given the frequency at the top is half a kilohertz, 500 hertz. I would convert that to radians right away. That would be one of the first things I would do. So remember that radians, we would, oh, sorry. Radians, we would have omega equals 2 pi times the frequency. So our omega is going to be pi. Pi kiloradians per second, because we're going to have 2 times 0.5 kilohertz. Remember, omega is going to be in units of radians per seconds, and your frequency is in hertz. So next thing to do is to look at the capacitors and inductors that we have here. So we have a 7 microfarad capacitor, a 200 microhenry inductor, a 600 microhenry inductor, and a 50 microfarad capacitor. So I would change all of these, and now you need to also remember what. So we have an inductor and capacitor. Your inductor is going to be J omega L. And your capacitor is going to be negative J over omega L, or 1 over J omega L. If you remember, 1 over J is negative J. And that's why the negative J is in the numerator here. Oh, yes, my bad. Thank you. 1 over omega, negative J over omega C. Thank you. So here we could just convert them. So we have 7 microfarads at the top. So we'd have negative J over omega 7 microfarads. Omega is pi kiloradians per second. 7 microfarads. Do that in your calculator, you'll get negative I I3 times. You get negative 45.47 J. And you can check that yourself. The inductor, we're gonna have 200 microhenries. So we'd have J omega L. We have pi kiloradians per second times our inductance of 200 microhenries is gonna give us 0.628 J. And we'll do you do the same for the capacitor and the inductor. I'll write these out since we've already done the first two, so I'll write these other two out. It's gonna, this one is gonna be end up at 1.885 J, and then the 50 microfarads will be J, should be negative 6.37 J. So it's good to, that's the first thing, you want to convert all of those. Now, let's see. Then we can rewrite the circuit, or we can see a couple things real quick before we, so I'd like to simplify it once before I rewrite it, just to see. And we can see here that these two elements here and these two here share something in common. They are both in parallel, not with each other separately. So the one red at the top and the one red at the bottom, they're parallel on their own, and they're all resistances. So we'll get a equivalent impedance. The first one, and since there are two, we can write this out. We have a 9 ohm that's in parallel with the negative 45.47 J. And then we can add these. That'll give us 8.66 minus 1.71 J. And then we also have the 1.885 J in parallel with the 2 ohms, which will give us 0.9408 and plus 0.9982 J. So I will rewrite these real quick.
If you want to spread out every single calculation from like capacitance or inductance.
No. As long as
you-
so I would show it once. Like the beginning, I would show converting. But every single time, like every single time you combine something in parallel, you don't need to write that out. and say there were like 5 capacitors, I would just show one. And then if you do all the other ones correctly. Yeah, right. Well, there could be in something like this, 5 capacitors would be no problem, right? It's just the equivalent impedance. You will not have to do a 5th order transient. That's no, that would be excessive. So I'm looking at this, and we got 8.66 minus 1.71 J and 0.628 J, 5 ohms, negative 6.37 J. Awesome. And now you would just kind of simplify this like any other circuit until you just get to one impedance at the end, right? So we'll see that these two are in series. So we simplify those, and then once you simplify that, you can see it's going to be in parallel with the next one, right? So those will combine into one source, and then that'll be in parallel with the 5 ohms. So these two are in series with each other, and so we'll combine turn into an equivalent impedance, and they're gonna look. It's gonna look like this with the 5 ohms. So that will be, those two will then be in parallel. I would rewrite all this out. The time I'm looking at.
The video she's showing like when she did the boxes, she was talking like Z1 or Z2.
Yeah.
Yeah, like just visualize.
Yeah, because since it's a combination, so the Z1 is like an equivalent impedance. The Z is impedance.
And when you write the bar on top of it, that just means it's a phasor.
Yeah. Well, then actually, yeah.
To get those impedances, for an inductor, it's J omega L, and then for a capacitor, it's negative J over omega T.
Correct.
Okay.
So I'm gonna keep the recording here going, but I'll go home today. I'll do the whole thing because we're not gonna get through it. So here we would simplify it all down. We'd end up with 2 impedances. Yeah. At the end, which would give us 0.9408 minus 5.36 J and 3.181 minus 0.144 J. And then those would be in series. All your steps along the way as well, don't forget to write your Z in. So we know what we're solving for. We know why we're doing this. And then you add these in series, and you'll get your final Z in of 4.122 minus 5.504 J ohms.
It's kind of like a hard feather.
Exactly. It's like a thevenin impedance. Exactly. And then you'd have 6.876 angle and 53.17 degrees. You can write it either way. I'll do this. All right, so that's what we just did. This will be easier now if I just go up through the. So this is kind of how it breaks down. Is that we have these two are in series, combines to one. This could be up here, down here, it doesn't matter. And then these two are parallel, combines into one source on the top, and then we just have our last. Oh, sorry, these two down here are in series as well. Yes.
You probably said this already before I came in here, so first you have to take the frequency and turn it into omega with T pi f.
Yeah.
Is that correct? Okay.
Yep, and that would be where I start with these. That would be the very first thing I do, and that is the first thing we did. We just inserted it.
So you got 1,000 pi rads per second for frequency.
Yeah, we just did pi kilorevs, but correct. Those are in series, then we get down here, and those two are in series. And we end up with our final impedance. Combining in series is that this just adds, so this would just subtract -6.37.
We're doing like combining in parallel, that division is important.
Yeah, so I did it with, since we only had two elements, you could do the multiply and then add on the denominator. If you had more than that, you would do it like resistances. Yep, exactly.
I started doing that with this one and it got extremely complicated, so like,
It does. I would just stick with two.
yeah, just, what do you mean? Oh, I mean like 2 at a time?
Yeah.
Okay, great.
Yeah, it turns into a lot of math. So, the next one is a first order transient. We look here. Sorry, with this one, you don't really need to convert that capacitor, right? This isn't going to deal with that phasor time domain conversion. So we want to start with analyzing it the three different main times we have. We have 0 minus less than 0, greater than 0, and infinity, right? 0 minus 0 plus and infinity. I usually start with 0 minus, and that's usually where you'd want to start too, is because when we do that, we can make some good generalizations. We can say that it's we can assume that it's been in steady state, that it is in steady state. So by doing that, we can change the circuit. So it's 0 minus the switch, right? If it opens at 0, that means it's closed, less than 0. So at 0 minus, we're gonna have this circuit here. The capacitor in steady state is gonna act as an open. Okay. And then the switch is going to be closed. And now we want to solve for V out of 0 minus. And another thing to notice too here is it's no longer V out of T, it's V out of 0 minus. You want to make sure we put in the time, right? And we said that T equals 0 minus. Denote which time you're working in. So we know here that it's in 0 minus and 0 minus. So there should be no ambiguity of what time frame we're working it with here. So there are a few different ways you can start solving this. The first thing I saw was we have a current source in parallel with a resistor. So that means we can do a source transformation. So we can convert that into a voltage source. Converting voltage source, right? We have V equals IR, Ohm's law. So we know that this voltage source is going to be 3 times 6, and then that resistor doesn't change. I moved the resistor up here and put the voltage source over here because visually, and you can see it, is that the voltage source polarity follows the current source. And moving it there, it's really easy to see which way it's going. Because if we wanted to put it down here, then you could start asking questions of, does it go that way or that way? But doing that is pretty easy to understand where it goes. If it was up here, then the positive would be going on this side. If it was up here, it would be on this side. And then that's where it comes into question. It's like, well, does it go up that? So I would stick to doing it that way. From here, these two are in series. That's simple, easy to find. And then you're left with an awesome circuit that really helpful to see. If you can see it, hopefully you can. It's a voltage divider. Right. The 7 and 6 are in series. So this is the voltage divider. So we'll have in the positive, the 18, those match up the polarities. So we'd have 18 volts times, sorry, that's a 5 ohms. 18 volts times 5 ohms over 13 plus 5 ohms, which is 18 times 5 over 18. So the 18s cancel and we're left with 5 volts. And that would be your 0 minus. The next part I would jump to would be infinity, because we know 0 plus from that, right? It would be, it won't change instantaneously.
When does it, when it's not on a capacitor?
Yes, so the voltage, so it would be the opposite of that. So voltage of a capacitor can't change instantaneously, but the voltage of an inductor can. And that goes back to our CEEBDT and LDIDT, DI over DT.
Current can't change instantly for an inductor?
Nope. Oh,
For an inductor, it's current,
yes,
right?
yeah, for an inductor, current, right, LDI over DT, and voltage can. So in this case, we had a capacitor voltage can't change instantaneously. So we know that at 0 plus, it will be the same as 0 minus. And that really helps us out. At infinity, well, you can already see it because I wrote it in the notes, but the switch is going to be open and the capacitor will be open again. We denote our time again. Make sure we do that. And since this is hinged, the big thing that's pushing the circuit is that current source, right? That's how we're getting most of what's happening. Well, that current source is no longer here. So if that current source is no longer here, then what's the voltage? What's the voltage drop here? If we have zero current. Zero, right? You can't have a voltage drop if there's no current. So no source.
Basically, everything, the 7 ohms and the 6 ohms and the 3 amp, everything y'all.
Yeah, so another way you could see this written out is if we redrew it again after removing those. I won't write the units. We would actually see it looking like this. That's what it would look like for the hinged part. And then this would be hinged itself too. So this would go away. And now you can really see that it's nothing, right? It's 0 volts.
We have to like write an IPQ for that or anything?
Yep, we'll get there. And now we need to find R thevenin. If you remember R thevenin, this comes up a lot as well. R thevenin, you do it at time greater than 0. And you need to make sure, so you do something to all your independent sources. And right, you kill your independent sources. Now, if your independent source is a voltage source, a 0 volt voltage source is a short. A 0 amp current source is an open circuit. So here back at greater than 0, we just get back to that hinge circuit. So really this whole half of the whole 2/3 of the circuit goes away, And we're left with something that looks like, I could have simplified it one more time. We're left with something that looks like this. Same with the impedance. You want to do the RTH, the arrow, so we know what we're looking for. So we're just looking into one resistance. That one resistance is going to be 5 ohms. So simply our thevenin resistance is 5 ohms. So now that goes to what you were saying, the writing out the equation. So we know that at 0 minus, it was 5 volts. 0 at infinity, it's 0 volts. And we know our thevenin. So we know everything that we need to know to solve now. So if you remember the equation, I'll go up here. The equation is V out of t is A plus BE to the negative t over tau. A solid question you could be given on the exam, just like a quick question, is knowing this equation. Knowing, being able to just write that. And just writing. So if you couldn't figure out anything else at the beginning or anywhere, write this down. That'll give you some points.
Would that be the solution for all the first order circuits?
Yeah, for these, yep, that's gonna be the characteristic. So you could do V out 0 or infinity. I'll start at infinity. So we know V out of infinity was 0 volts. So we can set that equal to 0. And then we could have 0 equals A plus B e to negative t over tau. Our t is infinity, correct? So e to the negative infinity is 0. So that whole b side, you're going to have b times 0, that whole b side goes away. And you're just going to be left with a equals 0, or 0 equals a. After that, then we can solve for 0. At time 0, we know that it's 5 volts. We know A equals 0. So we have BE to the negative 0 over tau, which is going to be e to the 0. And then anything to the power of 0 is 1. So B is equal to 5 volts, or 5. And that's because we know A is 0.
And you know that T, you can plug in 0 for T because it's the same as, oh, yeah,
Yeah, because we're, yeah.
sorry.
Nope, that's all right. That's all right. Yeah, and that's why we had infinity up here, and that's why this went down to 0. So now we know our equation is 0 plus 5e to negative t over tau. And the last thing we need to find for this equation is what tau is. And that was the whole purpose of finding our thevenin. And since we know our thevenin, we know tau is R thevenin times the capacitance. If you had an inductance, that would just change to 1 over RL, right? So we have our R thevenin times our capacitance. Our capacitance at the top was 9 farads. When you're really checking this out, you can derive the units of farads, right? Ohms, and 1 ohm seconds, second. And once you multiply it, you'll get 45 seconds. That's why that works. So your final equation would be V out of t equals 5e to the negative t over 45 seconds. And the last thing we'll do, and you'll have to do, is be able to draw it out. So drawing it out, we know our tau, right? We know we have our 1 tau, 2 tau, 3 tau. We need 45, 90, 135. Make sure you label your axes. We have our y-axis is going to be voltage, V out of T in volts. And we have our x-axis, which is T seconds. You know our tau, 45, 90 seconds, 135 seconds. And we can just start at our top voltage of 5 volts. You draw it, so your tangent line is going to be from that maximum 5 volts, and it's going to be straight down to 1 tau. Now, my handwriting is not straight, but that's the point there. And then you just follow the curve. The curve just needs to be like ballpark correct. It doesn't need to, we're not graphing calculators. That tangent line is important. You need to include that tangent line in the graph. And I would make sure it's dashed to denote that it is that tangent line.
Circuit Tutor gives us this formula for like the whole thing, where it's like V, well, this was of L, but like VL of infinity plus VL of 0 plus minus VL of infinity e to the negative t over tau. Like
that is basically what we did when we were
that's
solving.
like a more, I think yours fits more different types. This kind of,
That's the more generalized for
Yeah.
that type. So that equation you gave is doing this
yeah,
just in all one step.
okay. Do you think we should do this on the test rather than that? Because I feel like this you can catch errors more easily.
Yeah, this is how I've done it. This is how I do it. That circuit tutor equation is, I feel like that's more of just programming. It's easier to check.
Okay.
Because if you tried to do this in that program, it would be a lot of steps to go through.
Yeah.
So let me check. Sorry, you guys might have to go somewhere. So, I do have a couple more, but I will send out. So I have completed all of it. So I'll send it out. The next one I had is just mesh analysis. That's pretty simple, straightforward. It's exactly what you did on the first exam, but now you're doing it with phasors. And
This would be like right around the equation, but it's all.
yeah, exactly. And that's I put that up there. Just write out the equations. Make sure you have as many as you do unknowns. Here you'll have 4 equations, 4 unknowns, 5 if you include your SOT, the SOT variable. Thevenin and Norton. So those 2 are exactly like what you did on the first exam, but now you're doing it with phasors added in. Simplified, you'll get your 2 equivalents. I'll send this out. And then I put a second order here. You're not gonna have to do second order. I did second order just so I can show you the equations. You'll do a first order, and you'll run through. You need to be able to write the trial solution equation. I know how to do that. I'd also know A to the AE to the negative T over tau, what we did at the beginning. And finding this, you won't. So this is me explaining it. All you'll probably have to do is show that this is going to be equal to this. You'll just have to go from the second order to S squared plus an S. You remember doing that, writing the characteristic equation. So this is the whole like proving it, deriving it, which I was going to go over, and it'll be here. But you'll really just have to get from here to here to here. And then lastly, solving for S, which if you got a calculator, just put it in, right? So, all right, well that's all. All right, I wish I had.
Can I ask you a question?